Hi, friends of the sun. Welcome to our reading group. This is happening every Monday, and yeah, you can join it yourself. It's just on Zoom. And today we're talking about Kolmogorov-Arnold Networks, which I suppose is a pretty hype paper. And yeah, Ziming is so kind to talk about it with us. And if you want to join on Zoom yourself in the future, all the information for that is down in the description. And yeah, we'll see you, friends of the sun, on some Mondays.
Hi everyone, I'm Ziming Liu. I'm a fourth year PhD student at MIT in the actually in the physics department. But our group, me and my advisor Max Tagmark, are focusing a lot on the AI stuff. So my personal interests are like in the intersection of AI and physics. What it can be, physics of AI, trying to understand AI from a physical perspective, physics for AI, using physical intuition to build better AI models, and also AI for physics, like how can we build AI physicists that can, help us, act as collaborators or assistants to facilitate, scientific discoveries. So today, this Kolmogorov-Arnold networks were first, designed mainly for AI for physics, well, AI for science in general. But the problem scale are small enough such that physicists love dealing with toy models. So that kind of problem scales are more aligned with physics. Anyway, so without further ado, I I'm thank you so much for the invitation. It's my pleasure to talk about our recent work, um, Kolmogorov-Arnold Networks. So feel free to interrupt me because if you don't, I can talk about the whole hour. So this is the recent preprint we posted on our archive like 10 days ago, which caused some attention in the AI community. So here's the outline. I will first talk about math foundation and then some basics about how we actually implement this algorithm. And then I will talk about some, good features about CAN from accuracy and interpretability perspective, and finally followed by some, rumor that you might you might feel interested to hear about. Okay, so first math foundation. I simply cite this from Wikipedia, the Kolmogorov-Arnold representation theorem, basically stating that if f is a multivariate continuous function, then f can be written as a finite composition of continuous functions of single variables. That's quite important. And also the binary operation of addition. So this formula looks a little bit intimidating, but don't be afraid of it. I will give you a pictorial illustration in the next few slides. But the main takeaway of this theorem is that, in a sense, the true multivariate function is the sum. Say multiplication is non-essential. You don't need multiplication. Imagine you multiply two numbers, x multiplies y, you can basically read down in terms of log and exponential, then the multiplication becomes addition. And besides sum, the only other thing you need are just univariate functions. So this sounds like a very strong claim. I'll give you some caveat later, but so far it looks like a very strong statement. So how do we visualize? How do you actually visualize this representation? So to make things simple, let's consider we only have two inputs, and then the representation tells us the hidden layer 2n plus 1 now becomes 5, meaning that there are 5 hidden neurons in the hidden layer. So for example, for the first hidden neuron, it takes in x1 applied by some nonlinear transformation phi 1, 1, and also it takes in x2 applied by some nonlinear transformation phi 1, 2, and then sum up these two signals. And you did the same thing for the all other neurons. And finally, in your output layer, you basically it's a generative, it's basically a generalized additive model. Like you apply some nonlinear 1D transformation to these hidden activations, and then basically sum them up. So you can make it more intuitive by replacing this abstract 1D function symbols with this 1D curves, which, well, a lot of people like it. this is the only part that is not criticized by the public, that about the visualization stuff. Right. So this is naturally a neural network, because when you look at it, it has 2 input neurons, 5 hidden neurons, 1 output neuron, right? This is quite, reminiscent of a typical, of a standard MLP. We have 2 input neuron, 5 hidden neuron, and 1 output neuron. So we can abstract this, we can abstract this into a network, and even abstract this into layers. So this Kolmogorov-Arnold representation is basically a 2-layer cans with 2, each can layer is basically something like this, as I draw here. The first can layer has 5 inputs, has 2 inputs, 5 outputs, and second can layer have 5 inputs and 1 output. So once we have the notion of a can layer, it's easily to make it deeper by simply stacking more can layers. So here is just one example where we have 2 inputs, 3 neurons in the first hidden, 3 neurons in the second hidden, and 1 output. So you may be asking, why do we need a deeper networks? Well, because the original construction were just two layer. And so this is the caveat that coming along with the original Kolmogorov-Arnold representation theorem, is that although you can, construct inner and those inner and outer functions to approximate the original, continuous high dimensional functions, the inner functions can be pathological sometimes. It can be even but pathological. It might be, discontinuous or fractal. I hear some feedback. Is there a question or okay?
No, sorry
Right.
about that.
Okay, cool. Yeah. So a very simple example is, I give you this example, is exponential of sine of x1 squared plus x2 squared plus sine of x3 squared plus x4 squared. Then if you do the construction, you would realize that you would at least need 3 layers to do the square, to do the sine, and to do the exponential. So here is the training. Maybe I can start from the start. This is a very simple 3-layer can with shape 4, 2, 1, 1. And after training, you can indeed see that the unnecessary activations just disappear, and the solid diagrams correspond exactly to the univariate functions in the symbolic formula. So to make it more, maybe to make it more explicit, we want to compare explicitly between MLP and CAN. So for MLP, it's inspired, its math foundation is the universal approximation theorem, but for CAN, it's something different. It's the Kolmogorov-Arnold representation theorem. And if you write down the formula, you would also notice the difference, because in universal approximation theorem, it has this n epsilon trade-off. Like if you want to achieve up to some tolerance, some error epsilon, then you need to have a wide enough neural network. That is to say, if you want to achieve infinite precision, you need infinitely wide neural network, an infinitely wide MLP. But what's nice about CAN is that the theorem tells you, if you want to achieve, in principle, infinite precision, you only need a finite width neural network. Again, coming with the caveat that these activation functions may not be smooth. So that's actually one of the things that is, in some sense, sentenced, KART theorem into depth for like 20-ish years because of these non-smooth features. But as I said, our logic is that maybe we don't care about just 2-layer. We can easily stack the cans to become deeper, so the expressive power can grow even under the smooth conditions. Right. So I won't dig into the algorithmic detail, but just covering some basics in case you're wondering. So the way we model this 1D activation functions, so basically parameterize them as B-splines. So how does B-spline works is that you can imagine that you have some local bases, this bell-shaped thing, and they are translational, somewhat translational, invariant. They appear at different locations, and then your function is basically a linear combination of this localized B-spline bases. And what's nice about splines is that you can easily switch between different resolution. You can choose to go finer or choose to go more coarse. But this is a feature. But this is something that you can choose. Well, so for B,
wait a second.
okay, yeah,
See,
Hannes.
then if you go a slide back, what are we actually parametrizing in this B-spline then? Just the coefficients or also the locations where they have
Oh,
like the
yeah, great question. So so there are two things. So in training, by gradient descent, only CI, only the coefficients are trainable, and the grid points are fixed. But to update the grid points, I like for every 20 steps, I would do it in a non-differentiable way. I would basically just collect the distribution of the samples, and then reallocate my grids to make sure that my grids can cover the distribution. So so the splines have both grid points and coefficients, but they're trained or they're updated in different ways.
Okay, and like the coefficients you update with usual gradient descent, and then like let's say after 20 steps of gradient descent, it's kind of inefficient how we're representing the current function with
Yes.
the allocation, and there's like some optimization that's already known that you then apply to better allocate the locations of the basis functions.
Yeah, exactly. The subtlety about splines is that we need to deal with splines deal with bounded region, deal with bounded regions. But in neural network training, especially for later layers, the activations, the input activations can change. So we need to update the grids to accommodate to address this issue of a trainable range of a variable ranges.
Yeah, but right, there are also other like B-splines are not necessary, and you said there are already other.
Definitely. Oh, definitely. Yeah, you can definitely choose like Fourier, Chebyshev, any, orthogonal basis, and you can even replace it with a fully connected neural network. I mean, there are people, there are GitHub repos implementing that. It's a trade-off. Like B-splines, they're local. You can have gain some ability of continual learning, but it's very expensive to compute. But if you go with Fourier, then it's probably better because it's smoother. It's probably more, parameter efficient. But then it becomes more global, and you probably lose the ability to do continual learning. I mean, it's still quite open to like which activation function to choose, but but thanks, Hannes, for mentioning this. It's just a lot of there are just a lot of opportunities there. Yes.
And if we then use something like Fourier, then do we lose some nice interpretability options?
Yeah, great question. So when we say interpretability, interpretability is actually a quite subjective property. It depends on what your prior is. If you want to have as minimal prior as possible, I suggest using B-splines. For example, if you use Fourier, then you learn a sine function. You actually don't know whether it's really a sine function or is it because you put in the inductive bias because you use the Fourier basis. But if you are using B-spline and you still see after learning it's a sine function, then you're quite confident that it must be something meaningful. I will show an example to illustrate this later.
Yep.
Yeah. All right. Yeah. So B-splines, it's not necessary to stick to B-splines, but if you do want to use B-splines, I use this Bohr recursion formula, but it's very expensive because it's a recursive relation, and people have on GitHub have already figured out ways to make it more efficient, which I will not cover here. There are a few more tricks. that I want to confess. So the first trick is that I use this residual activation functions. The idea is basically that at initializations, the splines can be really bumpy. So if you stack a few layers of these bumpy splines, the initialization can be really bad because the initialized function can be really, really bumpy and potentially have optimization problem. So the way we solve this is that we add a smooth background plus some wiggly, spline functions, a little bit like residual connections. That's why we call them residual activation functions. And secondly, also a common problem is that we need to deal with initialization skills carefully to make sure that the activation functions are on the order, the activations are roughly the order of 1. So also, this is echoing back to Hennes's question, we need to update the spline grids to accommodate the fact that, to address the fact that, the activation range, they can change during training. All right, so that's what can is. So what can do, or what's the properties of cans? So the first property I want to mention is scaling. So people have talked a lot about either in applied mathematics or large language models that used in different contexts. People care about scaling behavior of a method. Basically, you have an approximation error or some any loss function L as a function of the number of parameters, capital N. And here, the dependence is a power law with some scaling exponent alpha here. So in classical approximation theory, if you have a d-dimensional function which has no structure, then, well, by no structure I mean has no compositional structure, but should have some smoothness structure at least. Then, if you use a d-dimensional splines of order k, and the grid points are placed on a uniform grid, then the scaling exponent is unfortunately need to divide it by d, which is known as the curse of dimensionality. But what's nice about Kolmogorov-Arnold is that the assumption is that if the function has a compact, smooth Kolmogorov-Arnold representation, then as we showed earlier, there's actually just summing and approximating 1D functions. There's no such thing as approximating high dimensional functions in CAN. Again, given the assumption that the ground truth is indeed having such smooth Kolmogorov-Arnold representation. In that situation, then D simply goes down to 1 because we're just approximating 1D functions. And then the exponent now becomes k plus 1, which is independent of the input dimensions. I will also give you some examples later. Right. So you might be asking, okay, your assumption sounds really strong, right? You assume that your task, your function can be complexly represented by smooth representations. But if there is no such thing that can be represented by the representation, though then the theorem is irrelevant and it's useless. But I want to show you guys that actually symbolic formulas that are widely used in science can actually be represented by the Kolmogorov representation. So the first example is multiplication, like when you want to multiply x and y. So we train a CAN to do the task, and you are realize by reading the graph. Well, I should include the formula here, but if you read it for a minute, you'll realize that it's actually doing like x plus y squared, and then minus in the parenthesis x squared plus y squared. So it's finding this interesting way to compute multiplying two numbers. And if we take the division of two positive numbers, it's more aligned with what we expect, is that it will learn the logarithm representation first, subtract them, and then take an exponential. well, there are more examples here, but the basic idea is that, well, so yeah, the last one I want to highlight is the special function one here. What distinguishes between cans and symbolic regression is that cans are intrinsically, a neural network which approximate things numerically. Well, you can afterwards, snap those activation functions to be symbolic, but even if they are not symbolic, you can still get quite good approximation of the target function, like the really highly oscillating weakly Bessel functions here. Cans can learn it. Yeah, so here are just some examples to show that our previous theory is actually reasonable. So here we tried 5 sympathetic examples which have 1D input, 2D, 2D, 100D, and 4D. So in almost all cases, it scales as n to the minus 4. The test loss measured in RMSE as against the number of parameters, the scaling, it scales as roughly n to the minus 4, which agrees with the theory. By contrast, the MLPs, scales worse and plateaus early. Maybe one example I want to highlight here is well, 2 examples I want to highlight. The first one is second to last. You see that for cans, it also plateaus in the end. Well, this has to do with the data size. Actually, the data size is just 1,000. So if you increase the data size, can further become better. And for the last one, I have used this example to argue that we need a 3-layer can, and indeed a 3-layer can has this -4 scaling law. But if you stick to the original can, which has 2-layer, then you see that it behaves quite worse. So again, this adds in a little bit subtlety in practice, because in practice maybe we don't know the compositional structure, like how deep you want to go, but you can try deeper. This is like the wisdom of deep learning, right? You may not, some functions may not be well represented by shallow networks, but maybe well represented by deeper networks. So the subtlety of shallow versus deep in MLPs or in traditional deep learning can still applied here and make this story a little bit more intricate. So for symbolic functions, you may say that, well, they are quite contrived. What about functions that we don't know there exist Kolmogorov-Arnold representations? And this is exactly what I show on this slide, is special functions. So for example, we take the Bessel function, which is the j nu x. We take in the nu and x and want to predict the value of the Bessel function. Then we don't know if there exists such a representation. But in either case, but anyway, we compare can to MLP, finding that can approximate better than MLPs. And even what's interesting about it is that the scaling laws, although not always being -4, can tell us something interesting about the function to be approximated. If you look at the spherical harmonic here, M0, N2, the scaling is -4, indicating that this function must have some interesting compositional structure to allow, a compact, smooth Kolmogorov-Arnold representation. But to compare this, M2, N2 spherical harmonic has scaling law -2, which is a little bit unsatisfactory. This basically means that this function is not that functional, compositional. But this is the bound one can get from just approximating a 2D, smooth functions, but with 2D splines without leveraging any structure. There are even more unsatisfactory scaling laws for the KV, which is another special type of Bessel function here, is that the scaling law is actually -1, which is even worse than spline interpolation in 2D. But MLP performs even worse. So it's something like, maybe for some scientific tasks in 2D, these neural networks can suffer from optimization issues, can even, underperform than Valina spline interpolation. So this is something to be remembered, to be keep in mind, like for science and for standard machine learning, like vision and NLP, these user cases, because they have different scenarios, so maybe the tools used in standard machine learning may not be directly transferable to the scientific setup. Yeah, just for more examples, we show that for the PDE, can also outperform MLP, but this is still quite preliminary results, and more tests that need to fully investigate the boundaries of CANs and MLPs. Maybe in the future we want to combine CANs and MLPs in some way to gain the best of both worlds. But one thing can do, but MLP or other non-interpretable methods cannot do, is to extract the symbolic formula. Like for this PD, the ground truth, actually not this PD, this is a separate question, but in both cases, the solution actually is a symbolic formula. So if after training, we can regress out the symbolic formula and then do further training, well, we'll see that the loss function can actually go down to near machine precision, which is quite awesome. Well, again, this assumes that there is indeed a symbolic formula underlying it. Well, so the first part is about accuracy. Let me jump to the second part, interpretability, which is actually the main part that I want to argue for AI plus science. So I've showed this plot before, but I want to bring it up again. Basically saying that if a can deal with supervised learning scenario when you have n variables x1 to xn and you have one target variable, well, you can easily generalize to more output variables, but for simplicity, assume we have one. Then the supervised learning task is that we want to find a mapping from x1 to xn to map it to y. And of course, you can use an MLP to fit this, but it's probably not that interpretable. But CANs here can, because CAN it's quite aligned with the compositional structure of symbolic formulas. It cannot only learn the compositional structure, but can also learn the univariate, activation functions quite well. Besides supervised learning, we also have this unsupervised learning setup. I probably don't have time to dig deep into that, but the formulation is that usually, well, in some cases, we don't have clear partition of input variables and output variables. We're basically just given n variables, and they may be, they may have the equal footing. They are, their rows are, equivariant in some sense. So in that case, we simply want to understand, the correlation or the interrelated relations of these variables. So we want to find an f such that f can map all these variables to 0, but the f itself should not be a 0 function. Otherwise, it's a little bit trivial. So one case of this scenario is that suppose we're given 6 variables, and the first 3 variables has this relation. x3 is exponential of sine of pi x1 plus x2 squared, and x5 is x4 cubed, and x6 is independent of all others. So from the construction of the data set, we know clearly that there are 2 groups of related variables. One group involve x1, 2, 3, another involve 4 and 5. And we want to use see if can rediscover this relation, and it is indeed can rediscover this. The solution, how we solve this problem, it's a bit technical. If you're interested, we can chat later. Well, so this is the part that attract a lot of criticism, but also a lot of praise, depending on your view. But I'm personally quite proud of this part. Well, it might be a little bit, too catchy, but this is the intuition. This is my mental picture about how I see CAN. So I think the reason why large language models are so transformative is because they're useful to anyone who can speak natural languages. However, the language of science is functions. Well, you can make it more advanced, like operator, but the basic object is functions. Cans are composed of interpretable functions. So when a human user stares at a can, it is like communicating with it using the language of functions. So I'm not sure if you guys have watched the tri-solar system, but it's how the tri-solars communicate with each other by just reading each other's mind because their minds are so transparent. So again, this is like when you read the can's mind, it's like communicating with it, and you can even put in your inductive bias into it there are some functionalities which allow you to do so, to fix some activation function to be symbolic, further training, do fine-tuning, removing some nodes or edges, like to allow you to really interact with cans. Well, and the last thing I want to say is that, well, do we want automated AI, fully automated AI, or an AI that is interactive with human scientists? And I would prefer the second one, because I think scientists in different fields may feel differently about which functions are simple or interpretable. So as a result, we should let human scientists to decide how they interpret Kant's results instead of given an inductive bias for them. Yes, so ideally we want Kant's to be humans can easily interact with it. Well, not only Kant's, but I more want to sell this paradigm, like human scientists can interact with a interpretable and interactive AI that they can jointly collaborate to discover something meaningful in science. Here's just a quick example of how human can possibly interact with cans. So suppose we're interested in this 2D symbolic regression case. So we're given this can, and the first step is just to train can with sparsification. And then you notice that there are 4 nodes which are actually useless, so you can actually prune them away, and you got this compact representation. And then just by naked eyes, you may observe that, oh, this is a sine function, so you may want to set it to be exactly sine. And oh, this is a squared function. You want to set it to be squared. Oh, this is something like an exponential. You set it to be exponential. And after that, all the remaining parameters are the affine parameters in the input and output. So we further train these affine parameters, and we can reach machine precision. And then you can explicitly write out the symbolic formula, which is exactly the original formula. So this is just one example of how you can possibly interact with Can to discover something meaningful. But this is actually quite simple example. You can in principle automate everything without human intervention. But in more complicated scenarios, or in cases where Can does not capture human inductive biases, it's better to involve human in the loop. All right, so that was just a very simple toy example, but we did a more advanced example, which is the example used in DeepMind's Nature paper 3 years ago, the knot theory example. Well, the math, actually, I don't understand the math. My collaborator taught me about this, but the basic idea when we formulate this into a machine learning problem is that you have many variables. You have 18 variables. One of them is called signature, and you want to predict signature from all other 17 variables. So what DeepMind did was they used attribution methods to identify important relevant variables. This is what AI did. And the second part is done by humans. They come up with the slope concept and prove it to be correct. So we asked this question: can we rediscover these results with cans, with more automation, with more efficient networks, more interpretable? The answer is yes, we can. So the first question: can we rediscover the results? Can we rediscover the dependence results? And surprisingly, we just train a can with just one hidden neuron, and it can already does this task quite well with 82% accuracy. It's reported like around 80% accuracy in the DeepMind paper, so it's competitive. It's a bit surprising. You can just achieve the same level of accuracy with just a really compact CAN network. Well, but someone well, yeah, but people from like the Shi lab from Georgia Tech, they find that actually you can have just a 60 parameters MLP to similarly achieve 80% accuracy. So this is also surprising to me. I think this seems to imply that the knot dataset is actually not that difficult, and so I think this is not a bad news for CAN, but I think this is a good news. This is optimistic for AI science in general, because this means that for many tasks, including the knot theory, you actually don't need to run a large model to do the task. You can just take a small model, and small models are actually more likely to be interpretable, either the small model being MLP or CANs. But it's still not known whether MLP can achieve the same level of interpretability compared to CANs. But again, interpretability it can be quite subjective. So at the end of the day, it's up to the human scientist to determine, okay, whether this is something meaningful or not. All right, so we can rediscover some formulas the DeepMind posed, not exactly, but something similar structure. And what's nice about CAN is that you can easily trade off between symbolic formula, the complexity of the formula and the accuracy of your formula. And beyond that, we also showed that, well, something that DeepMind did not do is the unsupervised learning. Well, we just treat all 18 variables on the same equal footing, and then trying to discover their interrelated relations. So by training 100 neural networks, we noticed that there are 3 types of CANs after training. The first type has a strong connection coming out of signature and also some other variables, which is exactly the signature dependence relation investigated in DeepMind paper. So it's amazing, even in this unsupervised learning setup, this signature dependence can still pop up. And what's nice about it is that for the second and third appears quite new to me. I was thinking that we discovered some new math from the data set, but then my collaborator told me that the second relation is actually just a definition of the cusp volume. So by definition, it's correct. But it's still nice to see that it just naturally emerges from CAN training. For the third relation, it's more it's less trivial, because my collaborators even spent some time digging into literature and finally realized that this is something known in the literature, that is one variable is the upper bound of another variable. Right, and we also did some physics example, but maybe I don't have time. Yes.
Let's first, before we get to that one, go through some questions in the chat.
Sure.
So,
Yeah.
one question would be, do you have something to say about generalization instead of just expressivity?
Oh, that's a great question. So, I think so we need to distinguish in distribution generalization and out of distribution generalization. So for sure, like other deep learning models, out of distribution generalization is not guaranteed. You need extra domain knowledge. So, but for in distribution generalization, it depends on, so like in classical statistics, we have this bias variance trade-off. So again, if you need to choose an optimal architecture, which have optimal expressive power to achieve the best generalization error. So it's a bit like the U-shaped thing in bias variance trade-off. And we observe the same thing where you make your CAN network more grid points larger and larger. So we observe the same thing. I hope that answers your question.
Yeah. And can you also say something about the spline parametrization, if we now have like what types of functions, right, we can represent, and how do you call it bounded? No, not bounded. If you go into the x minus infinity direction, what the value of the spline becomes?
Oh, great question. So that is because splines are bounded. That is another reason I include this residual activation functions, because I chose zero boundary condition. So if you go outside the boundary becomes zero, which that does not make much sense. Well, maybe it makes sense, but it's just that it does not have any gradient in it. So it's also another reason why I need to include this basis function to make sure that because the basis function can also handle things that outside the boundary.
And then, okay, thanks. Then we actually had the comment in the chat that someone should try cans on MNIST. And yeah, I found that interesting and funny because we also talked about that a little bit in the group meeting. But anyway,
Yes.
let me see, let me scan a little bit. Yeah, so right, this I think goes a little bit along my notion of where cans could have an advantage if you replace MLPs with them. With, to be clear, I think is not the main purpose of cans, and I think is also your notion that it's not what you're trying to use cans as, and how you think they're the most useful. But where they can have an advantage in replacing MLPs and being more easy to optimize is, I think, if we know that the prior of the splines or whatever function you use to represent your intermediates is close to the solution. And we know that we have somewhat of this type of form in the problem that we're trying to solve. And maybe that's the case in some of these simple physics problems where the inputs already have a
Yes.
very your
Yes.
interpretation.
Yes. So I would imagine that for physics problems, because physicists already extract out the most important physical parameters, so there's no need to extract out from raw data. But if you're dealing with vision data, language data, graph data, you probably need something to extract out the key variables into latent space, and then maybe you can in latent space and then map something out. Yes.
But I think you might be a little like we can't just say for physics problems, right? Because maybe for the type of physics problems that you're dealing with, this is the case. But of course, we also have something like we just have structure of a molecule and a protein.
Definitely. Yeah.
People also call this a physics problem, right? And then trying to predict some energy for it. And there we again have to extract like
Definitely. I would
physical
include that as
data.
a physics problem, as long as, I mean, well, yeah, maybe I think the point is whether your variables are raw or more physically meaningful, but that's a little bit subjective. but the point is that cans are good at dealing with physically meaningful variables, whatever they are, but not that good at dealing with raw data.
Okay, and have you seen something like people using cans for solving PDEs or putting it into these neural PDE solvers or something like that and being especially successful?
Well, it's too early to say that, but
Okay.
but the early but here, because I skipped this slides real quick, but this is just one preliminary example we had. It's a really simple post-one equation, but yeah, that's our first attempt. It looks promising, although the training is slower than MLP, but the accuracy and parameter efficiency seems higher.
Okay. Is denn something? I guess these questions are mostly answered. Let's maybe do the following. Let's maybe do Tathagata. Can you ask your question? Or yeah, go ahead.
Yeah, I have one more question, so I decided to unmute myself. Thanks for the very nice talk, and thanks, Hannes, for arranging this thing. So I have a question like towards more practical things. So I was looking at the implementation where there is something like grid resolution and stuff like that. So when you say grids are updated in the process of training, so does it mean only the grid positions are updated, or also it is like resolution as well? And also, like, what could be a kind of rule of thumb to choose initial grid resolution, if you have some comment on that?
Okay, yeah, great. So basically, we can take the intuition from a spline interpolation. So suppose you have 1,000 data points, then you probably want your grid points to be a little bit smaller than that number. You say like 200 might be good. But because Can sometimes have optimization issues, so you probably want even smaller, like 100 or just 50. So it's advisable to start from a small grid point, like start from 3, just in case to avoid optimization issue. And then after you go to high precision, you gradually make it finer and finer. That's my rule of thumb, but may might be only applicable to my cases. In general, I think more experiments needs to be done to verify this.
I see. But when you say coarse to fine kind of thing, like coarse grid to fine grid, does it happen automatically in the training
Oh,
process?
it doesn't. Yeah, no, it doesn't. You need to manually do it. You can initialize a model called initialize from another model. That's what the function that's what the API name is. You can use that one to initialize a fine-grained model, and like to initialize a fine-grained model from a coarse-grained model, and then you further train the fine-grained model to reach higher accuracy.
And what do you mean by
Well,
initial? Is it from coarse grain? Like, do you need to do grid interpolation for that? Do you mean like that, something like that?
so
Something like
let's
that.
start
Yeah.
let's keep it at that, because we have many questions and want to also
Sure,
get
sure.
to hobbies, for example, and to some in the chat. And yeah, let's do one more in the chat. And so many people are interested in if you are able to comment on people saying that you can rewrite cons as an MLP with some repeats and shift before ReLU. Do you know what what this
Yeah. Totally.
comments
Yeah.
comment on that?
So if you consider from the approximation perspective, from the expressive power perspective, that's true. Well, if you think of even, from an even higher level, anything that can guarantee universal approximation, any machine that built out of it are just function approximators. But from the technical level, I agree that in principle you can do that, but then it becomes less interpretable. Well, you may gain some accuracy, you may gain some efficiency out of it, but I mean, it's a bit subtle. So when we talk about deep learning models, we not only talk about expressive power and approximation ability. We also talk about generalization, optimization, and the interpretability. So I'm not saying that can excel at all other, can excel at MLPs on all aspects, but I just want to highlight that cans make interpretability and some cases reaching high precision super easy. I'm not saying that you cannot do that in principle with MLP with a lot of efforts, but it's just that can make it easy to do that. So here also has a notion of computation complexity, in the sense that when we make this scientific discovery, again, I'm trained as a physicist, so like my mind are a little bit inclined to the scientific discovery. I think cans can make discovery easy, although in principle, as the argument says, MLP are equivalent to cans from the expressive power perspective. It's possible for you to do the same discovery with an MLP, but it's just way harder to do that because MLPs are not designed to be interpretable, but cans are designed to be interpretable. So maybe my answer is that from a practical perspective, they have differences. And that's enough because we care about practice. We care about what this models behave in practice. But you may have a unified theory that unify MLP and cans, and I'm more than happy to see that happen because I'm a physicist. There's nothing more that can make me happy is to see a unified theory and showing that my thing is just a special cases of a more grand theory, and also connecting what the special theories are connected.
Okay, very nice, very nice. Then I would suggest, do you think there's like more slides that you think are core and we should cover?
There's some rumor or anecdotes. If you guys think, I think it's interesting to talk about that. Maybe just 5 minutes if you
Yeah,
give
let's
me.
do that. And
Yeah.
then to the people that have questions, maybe also Ravi and Amin, just write a one sentence summary into the chat and then you can ask them yourself in person. But if you have questions that haven't been answered yet and up to Malachi in the chat, then please write them again and we can see the upvotes that each of them get again. All right, let's go.
All right. Yes. So I think this is also related to what people are saying that MLP are cans are just MLPs. So the question is, what's the novelty of cans? So from a technical level, what makes a can a can? What is a can? So can has learnable activations, which is not a new idea. People have spline networks, have kernel machines. Cans have activation functions on edges, which is again not new. The two-layer Kolmogorov network already do that. Although, our writing make it more explicit in that case and contextualizing contextualizing in more than deep learning. Cans are deep, more than two-layer. That's for sure not novel because it's all about deep learning. It's all about stacking more layers. Well, so if you want to obsessed with then what is new? Then I have to say that the combination of all three properties is new. You may say that this sounds like x plus y plus z, but it is. I have to confess it is. So cans have learnable activation functions on edges, which can be made deep. This is the combination that has never encountered before. And because of its making deep, it has some potential that is not possible before. So from a sociological or from a practical level, I think it's more proper to answer this question from a practical or sociological perspective. Dating back to 1974, like our situation is a little bit similar to Paul Werber's, when he and his advisor realized that although a two-layer perceptron cannot do XOR quite well, a multi-layer perceptron can do XOR. Although back then their application was basically for politics and sociology. That was why their work did not attract much attention back that time. And we simply saying that, oh, we can extend the two-layer Kolmogorov network into deeper. And this can lead to more accuracy and interpretability than MLPs for small-scale scientific problems. If we were like 30 years ago, our work are very much likely not being noticed at all because AF science it can be a quite niche field. But because of today's social media or anything advertising, it just becomes catch more people's attention. But if we compare to history, this is not the first time that such thing happens. Well, also people ask, okay, Hennis, yes.
No, let's do this slide first and then get back
Cool.
to the Anderson localization example, maybe.
Sure. Actually, I want to skip the Anderson localization, but Ravi, do you have a question? You can unmute yourself.
Thank you. Yes, Ziming. I did have a few questions. I hope they can be answered. First things first, Ziming. Thank you for your talk. I'm really enjoying your presentation. I'm really excited about Cannes. I just wanted to ask maybe up to 2 questions. Um, please forgive me if they were already discussed. Um, my first question is, back then you were talking about scaling laws. So I'm trying to understand, like, how come neuroscaling laws are important? Like, how did they give Cannes an advantage over MLPs? Because back then, with MLPs, I don't remember talking about, we discussing about neural scaling laws. And my second question is, and this might be a shot in the dark. Do you see DeepMind making use of Cannes? Those are my only 2 questions.
I see. So first of all, why neuroscaling law matters, at least recently, is the mentality of scale is all you need, with the argument that you can just scale up your model without carrying too much fine-tuning about the structure, and you can magically get a better performance. So if that's the case, then people would just rush to build larger and larger models. But also the scaling exponents, like how fast the scaling law scales, matters. And here we show that for simple this symbolic formulas, cans have steeper scaling laws than MLPs. This is not directly relevant to the setup of large language models, but at least in high precision scientific machine learning, it's relevant, because where people want to calculate something as accurately as possible, and we want to understand how much compute or how large model we want to build in order to like how large model, how much compute we want to invest in order to achieve, say, 10 to the minus 7 accuracy. And that's something the scaling law can tell us. And then second question, the DeepMind, honestly, I don't know, because have only exist for like 2 weeks. And I don't have any inside news, sorry.
That's fine. Thanks, Ziming.
Yep.
Okay. Then maybe I think the one slide after so what are cons good and bad at? That's maybe a good summary to go through.
Yeah, sure. Yeah. So I can continue on that. Okay.
Yeah, and by the way, right, we don't have time limitations here.
Okay. You do not have a time limitation.
That's
Okay.
right. That's right.
Okay, cool. Yeah. So again, I'm not claiming that cans outperform MLPs on every cases. They must be good at representing different classes of functions, and there might be some overlap, and they themselves may have some good functions to represent. So to illustrate that, to demonstrate that, we can just do a thought experiment, which are like physicists or scientists' favorite thing to do, is that you don't do the experiment, you just do a thought experiment. Okay, so let's assume that we have a teacher-student setup. So for a task generated by a teacher the student will be more likely to perform better than a student MLP. And then for a task generated by a teacher MLP, it's more likely that the student MLP can perform better than a student can. So the real question, which is quite philosophical, is that what is the network? Or if there is a god that make up the whole world, or like the physics that generate the whole universe, what is the network they use to generate science, vision, language, whatever task that you care about? So in the end, I think this is all about inductive biases. A network performs well for a task if the inductive bias of the network agrees with the inductive bias of the task. And the reason why cans are good at science is because science are described by symbolic formulas, have nice modularity, compositional structures, and this is exactly what cans are good at, because cans are simply summing up. The summing is the interaction between different variables, and 1D are simply like local interactions, something like that. So quite aligned with the inductive bias of science. But it's hard to say whether Kant's inductive bias are aligned with vision or language. Well, yeah, maybe we also learn something from history. in history of learning, machine learning, even before the term of machine learning is coined, well, AI is coined way early than machine learning is coined, but there's this swing back and forth between symbolism and connectionism. So in 1958, Frank Rosenblatt invented the first perceptron, showing that it can do its classification on separable data and also can do some psychological experiment. But then 12 years later, in 1969, Marvin Minsky and Samuel Papert wrote these books on perceptrons, but actually critically criticizing that perceptrons cannot even do the XOR operation, which is sort of sentenced perception to death, and also implicitly leads to the death of Frank Rosenblatt, which is very unfortunate. And then in 1974, as I mentioned earlier, Paul Worbus successfully extended a two-layer perceptron to multi-layer perceptron and find that multi-layer perceptron can indeed do XOR. And then in 1975, Robert Hatchett Nelson invented this, coined the name, the Kolmogorov networks, basically written down, parameterized the network, the Kolmogorov-Arnold representation as a Kolmogorov network. Back then, still two-layer with 2n+1. And then George Seibenko in 1988 said that a two-layer Kolmogorov network can do XOR, which is good, which may give you the sense that you do not need deeper Kolmogorov networks to do the task, because two-layer MLP cannot do XOR, multi-layer MLP can do XOR, but a two-layer can already do XOR. So maybe you can just stop there. You do not need to advance further. But unfortunately, in 1989, Tommaso Poggio said that Kolmogorov-Arnold representation is irrelevant for neural networks because of the pathological behavior of your inner functions. They can be very non-smooth. So that is basically the winter of the Kolmogorov-Arnold network. That's basically, I guess, why people are surprised that why the idea of CAN is only, appear today, not before. It should be appear way earlier than 2024. So that could be one of the reasons that Kolmogorov-Arnold was deemed as irrelevant, hence practically useless by top scientists. And then 2020 and then 2012 is, you can say, is the first year, the year of modern deep learning, and everything from it, basically starting from the connectionism. So if you notice, the pattern is quite interesting, switching back and forth, first from connectionism, and then people's criticism make sentence perception to death, and then symbolism win back, and then again the Kolmogorov-Arnold networks swing back, connectionism, and then a symbolism come back because Kolmogorov-Arnold representation was sentenced to death. And today's deep learning was basically based on connectionism. And we don't know yet about the future. But for me, I think CAN is kind of somewhere in the middle of symbolism and connectionism. Actually, I think two-layer Kolmogorov networks are closer to connectionism if your task is actually needs very deep compositions. If your task is very complicated, needs a deeper CAN, but you only have a two-layer, then your two-layer network will basically behave like a kernel machine, which is not that interpretable. That's why I count Kolmogorov networks more close to connectionism. But CAN, thanks to the expressive power, because of the depth, can somewhat balance between connectionism and symbolism. I'm not sure if it's something to be brag about, because I more deem it as a feature rather than an advantage or a bug. But it potentially can bridge between symbolism and connectionism in a more effective way. And maybe we do not need to be, treat symbolism as enemy, and symbolism doesn't need to treat connectionism as enemy, because hopefully these two paradigms can be unified soon one day. Well, maybe going to a higher perspective, and people ask, what's the real difference between CAN and MLP? And I want to go bold here because I just come up with this idea like 5 days ago. So I want to go bold about it. So please correct me if I'm saying nonsense at all. But to me, I think from the philosophical perspective, Kant versus MLP is really reductionism versus holism. So by reductionism, reductionism is quite prevalent in science, especially in physics, where no matter how complicated the world is, the system is, we believe that we can always decompose this very complicated thing into separate objects, plus some simple interaction between these objects. That's the idea of reductionism. In contrast, holism saying that, oh, we don't, it's too hard, it's impossible, and we don't need to disentangle the whole thing into different parts. The whole thing, like each part is not important at all. What matters is how these parts interact with each other. So so from this perspective, this distinguishes the goal of Kant's, the philosophy of Kant's and MLP. So for Kant's, because each activation function is learnable, this kind of highlights the importance of each individual part, plus some simple interaction between each individual part. Well, for MLP, the philosophy is that, well, we can make each fundamental unit quite simple. It's just have fixed activation functions and with linear connections, something like that. But what's important is that you have many neurons that interact with each other, although the details of one single neuron may not matter that much. So that's the idea of MLP. So from this perspective, this may also, this is not just a philosophical game, but this may give us some insight. How do we build models in the future? Because reductionism and holism, they are not necessarily contradictory to each other. There are ways to reconcile and to combine these two, philosophical beliefs. And the same thing happens if the same thing could happen if we try to come up with a model that combines Kant and MLP, even on this philosophical level. That could be quite interesting to try. And there are also people asking, are Kant's natural? The first question is, are Kant's physical? So unfortunately, Kant's are less physical than MLP, in the sense that if you consider physical to the Feynman diagram, which basically we have some incoming particles, and then when they collide, they produce some complicated, interesting phenomenon, and then they bounce back, creating new particles and scattered away. So in Feynman diagram, the edges are really boring because it's basically just a particle propagating in space, doing nothing. But on the nodes, it's on the nodes that interesting physical phenomenon interaction happens. So that's more aligned with MLP. Well, but it again depends on the interpretation, like a representation. You may find another representation where the particles, they themselves evolve, but their interaction can be quite simple. Although we are more familiar with the representation where have the particle representation, and the interaction can be quite complicated. And also people ask, are Kant's biological? Because when we say neural networks, we kind of imagine that they are inspired from the brains, the neurons in our brains. But indeed, there's something like cells in our human retina which actually behave more like Kant's, which apply activation, nonlinear activation first, and then do summation. Well, there are also some anecdotes behind the scene, like how we went about developing the idea. Actually, there are more plot twists than people would imagine by just reading the paper. So first, like 2 years ago or even 3 years ago, I think if we have learnable activations on nodes, it should be more interpretable. Well, again, my goal was for scientific tasks back then, and then I tried some simple examples, but only the simplest examples can succeed. But you just add a little bit of complexity, it just, does not work. So I just abandoned this idea. And then early this year, well, in a conversation, my advisor bring this again to me that Kolmogorov-Arnold theorem is irrelevant for machine learning, and I kind of want to be rebellious. I want to be the I want to say because you say it's irrelevant, I want to build something that's useful in practice. So that's how I start this project. But at the early stage of the project, it's not immediately clear how to set the width of the network because the representation tells us it's 2n+1. Well, so for programmers and for people in machine learning, they may think that it's very natural to have a tuning parameter, but sometimes for mathematicians and for physicists, we're too constrained by the theorem. So it takes us for a while to realize that, oh, we can generalize it to arbitrary width. It can be wider, and it can also be less wide. Well, and the biggest challenge is that how do we actually build a deeper cans beyond 2-layer? That's actually not clear at all at first, although the way we present in the paper makes it seems quite convenient and straightforward. But the first CAN network that we build were not even efficient in principle, in that we noticed that the outer functions have 1 index and inner functions have 2 index. So we just generalize it to, like, if we have n layer network, then we probably need n indices for the last layer, for the most inner functions, which is impossible to scale at all. Only it was not until later did we realize that the outer functions, they secretly have 2 indices with the output as 1 secret index. So after we realized that, we realized that, oh, actually both inner functions and outer functions are tensor with 2 indices, which is basically like a neural network layer where we have some input and have some output. Right, I'm basically drawing to an end. So there are already some nice GitHub repos contributing to the space of CAN. So my original offer also referred as the vanilla implementation. I would still say that it's good for interpretability. If you care about small scale problems interpretability, I still suggest that you use my repo. But if you don't care about interpretability, or your problem scale is just too large, where you care about efficiency, you may use efficient CAN instead. There are also fast CAN, shapeshift CAN, which basically deals with the problem of efficiency. There are also CAN for graph, CAN for reinforcement learning, CAN for large language models, CAN for time series, CAN for image, CAN for PDE, CAN for diffusion, CAN for OD, everything. And there also, as we chatted earlier, you can try different activation functions, and there are also people trying to make it try to write a CAN package in different language. So yeah, this is my last slide. So I'm quite open, and I myself are quite humble. I think it's quite unclear how big a role CANs will play in machine learning in the end. Like, practice is the only criterion for testing understanding. If you say CAN is good, you need to, like, I need to propose good examples to show that CANs are indeed good. If you say CAN is bad, you also need to do experiments to say that. And it's my initial motivation, like, I'm trained as a physicist, and my research previously was basically in the intersection of AI and science, specifically physics. It's my initial motivation to make CANs a niche tool for AI plus science, and I will still stick to this goal because I also feel like if I want to do machine learning, I do not have any competitive edge compared to other people which can write out those efficient CAN, Fourier CAN GPT within just 1 day or 2. So I will again focus on AI plus science and make CANs a better tool for it. And I'm also not that personally attached to CANs because I think CANs can just be an intermediate product. And in the end, we may need something more powerful and more interpretable for science. But I'm still happy to chat if you are from a machine learning background and you're interested in applying CANs to your applications. I'm afraid I may not have much intellectual thing to say, but I'm happy to chat. Yes, so that's everything that I want to share today. Thank you for your time, and I'm happy to take more questions.
That's a question with regard to the difficult points you raised earlier.
Oh, sure.
Okay, so actually that was my question. You mentioned you were having difficulty determining how many layers, how to make deeper CANs. And so my question was how do you set the variables for multi-layer CANs? So from the appearance of the Kolmogorov-Arnold theorem, there are just 2 layers, and then intermediate layers would be 2n+1 nodes, and then the last layer would be n variables. And so when you stack them together, how do you pick the number of variables, and what are they?
A great question. So yeah, so in our experiment, if we aim for interpretability, I would choose the smaller possible network at first. If I find it doesn't work, for example, I just have 2 layers with 1 hidden neuron in between. And as you see in the knot theory, it already can achieve quite good accuracy. But if we care about, so for interpretability, I start from the simplest possible and then gradually expand it if its performance sucks. And for accuracy, because I kind of have a sense of how complicated my targets are. For example, we take the equations from the Feynman lecture notes, and this equations are not that complicated. So I just set the width to be 5, and I run all possible depths, including 2, 3, 4, 5, 6. I run many models and select the best model. I do not yet have a systematic way to determine that yet. And the reason why I choose 5 is because the composition graph are, I have a sense that it should be enough. And I'm less certain about the depth of the network, so I simply do a sweep. Yeah.
Okay, thank you. And the other thing is that you mentioned earlier you were researching the knot theory, and then you got an inequality. How do you represent the inequality in CAN?
Oh, that's something that is not doable with, and that is not feasible with CAN yet. But I more think this is not a problem with CAN or MLP, not specific to the model, but the problem of how we formulate the problem as an inequality symbolic regression. That's something I haven't come up with a good idea for that yet, but it sounds possible.
Oh no, but because I thought you mentioned you discovered the inequality in the rediscover the inequality.
No. So rediscover the slope, but not the inequality. Sorry that I didn't make it clear. Let's see. No, so indeed, they discovered the inequality. So they use AI to identify the important relevant variables. And they use MLP, and we use CAN, and they human come up with the slope concept, but CAN can discover the slope concept. They human prove the inequality, and we did not reproduce this part of their results in the CAN paper.
Oh, I see. Okay, and then
okay.
So back to the first. So thank you. So back to the first question. So when you set up the multi-layer CAN, are you let's say for the intermediate layer, the number of variables, are you just picking? You said you depend on your hunch, but the number of variables, is it when interact with, let's say, the second layer can, and then the third layer can. So that at the bottom of the second layer, is it the number of variables? Are you choosing as many as possible, and then each variable would be again, let's say, because the Kolmogorov-Arnold representation is for the function is basically each function is one variable at the as a functional value, and then you have the variables are n variables, right? So at the second layer, at the bottom second layer, you choose, let's say, m variables. So each variables you're again expanding to n variables, and then are they sharing the same n variable at the bottom of the third layer, let's say, for example. So you have if I can't do the graph, so is it the edges are like complete, let's say bipartite graph, each node at the top layer connects to each of every node at the bottom layer, something like that. I don't know if I'm making myself clear. Let's say look at the PPT, this page, the top left page, and then so let's say this intermediate second level 1, 2, 3, 4, 5 nodes, and then so these nodes, the number of nodes 5, it seems that and then does does each node on the third level connect to each node? So the second. Well, so the bottom level has 2 variables, right? So I'm just wondering how you connect each node. How do you make those?
It's fully connected. It's fully connected.
Fully connected.
It's fully connected. Yeah, it's fully connected, but it just naturally happen if you have some sparse regularization. It becomes, this sparse graph, but at initialization we want to put as minimal inductive bias as possible. So it's just minimal. It's just the fully connected is the minimal, maximum entropy choice.
Okay, thank you.
Thank you.
Hi. So
hi.
I had a query from a practitioner's point of view, in which if I try to scale it up with the transformers, for example, does that hold up?
You mean we want to scale CAN to the scale of transformer? Is that your question?
Yeah, using if we can swap out those layers with CANs, for example, and instead of applying on a toy data set, if we use some real world data set, then can that scale?
So in principle, well, there is already someone trained like CAN GPT on tiny stories. So admittedly, tiny stories is still a quite small data set, but I think it's promising. But again, it's something not my expertise. I'm not that sure about its efficiency, because when we talk about scalability, we care about, we are talking about efficiency. But it seems feasible to just replace the MLPs in transformers with CANs. You can do that, but I'm just not sure like how much advantages you can gain from that.
Okay, so you're not sure about the accuracy advantages that we can get out of it. Okay, thanks. Cool.
Thank you. Thank you.
Okay.
One more question. So earlier you said about the irrelevancy of the objection with the irrelevancy of Kolmogorov-Arnold representation. Is it because you said it was because the non differentiability of the representation?
Right, exactly.
Okay.
Yeah.
But then you use spline because we can always let's say the approximate in terms of say L2 norm or maximal norm.
Oh, I think the point here is that you can make a network deeper. So with a two-layer Kolmogorov network, you sometimes need non-smooth activation functions to be, to represent the function. But with a deeper CAN, you may be able to represent a function smoothly, which cannot be represented smoothly with a two-layer CAN. So I think the deep is the core idea here.
I see. So is it akin to, let's say you have a fractal function and then you just if you have a deeper layer, then you have a smaller scale, kind of the more of a nested resolution kind of thing, or?
Yeah. I think that's yeah, I think that's relevant. Although my picture is more about composition of functions, but maybe your picture is right in under some certain basis. It's like when you try to approximate something fractal, you would want multiple resolution, and each layer will add you go to finer and more finer grid. I don't have a good intuition for that yet, but I get your point. Yeah.
Okay, thank you very much.
Okay, then let's first get to two general questions from the chat, which gained some traction. I guess people are interested in some non-science stuff, and how long did this project take? What was the reason that you started it? And was it more of a main project, or did it like start from the side?
Sure. So yeah, I think these slides have answered some of the question. Like I started this project. Well, I first have the idea about learnable activation functions 2 years ago, basically try to motivate symbolic regression. I want to train a neural network which can give us symbolic activation functions to be interpretable. But then I realized that, well, this is still like MLP, but with trainable activation functions on nodes. That is called learnable activation functions in our paper in appendices, if you dig deep into that. But I found that learnable activation networks are not that interpretable because of the weights, basically. So earlier this year, my advisor mentioned this Kolmogorov-Arnold theorem is irrelevant again to me, and I want to say that, and I want to try my best to say that, oh, it can be useful. It's just that people did not, try hard enough. Or yeah. Anyway, so that's how we started this project, and that was like in January or February. So basically, I think, as you can see, well, most of my time I actually spend on, figuring out these trivial stuffs. I think machine learners think these are trivial, like how to choose width, how to make it deeper. But it did take us like around 2 months to develop, to conceptually get everything through conceptually, and also get a minimal working example. Like the grid update, at first I tried normalization layer, it doesn't work, maybe I didn't do it right. And then I also tried trainable grid points, but in the end I find that the update grid points is the best. So that's about the schedule. Like that's for the first 2 months, and then for the second 2 months, I reached out to some collaborators in science, the knot theory example and the Anderson localization example, just to push the limits of CANs, what can do, what cannot do so far on a more realistic scientific research setup. And that took me another 2 months. That's about the cycle. And for future, I think Can for Science is very interesting, and I would explore more, reach out to scientists to ask what questions they have that can be potentially solved by Can. But for longer plan, I have to be honest that I don't have a longer plan. I don't know, as I said, I don't know how much a role can play in the end. But I think it's more about for me, I think it's more about scientific curiosity to understand the strength and the limitation of cans. Yeah.
Did you come to Kolmogorov-Arnold theorem by happenstance, or you know it, or somebody mentioned to you, or you just know it beforehand?
No, it's hard to trace back when I knew it, but my advisor mentioned this to me like once, and I don't remember how many times, but basically saying that, oh, like theory is not that useful, Kolmogorov-Arnold theorem is relevant. Here is a, it's paper from Poggio et al. In 1989. So that's how I know this theorem, although my advisor was saying that it's useless.
I see. And so when you do the fitting, you use so basically it's a B spline, and then is it just optimization, normal optimization, or anything like back propagation or whatever? How does the fitting operation just
right? Actually,
sorry.
Yeah. So I first tried some kind of normalization, but that doesn't work very well. Maybe I didn't do it well, and then finally I realized that do the grid updates on the fly, like for every 20 steps, make it work. So there's no particular way. So like the current implementation doesn't need any way to normalize data because the grid update can handle it.
I see. And is there any procedure like back propagation, or just
it's just vanilla backprop. There's no fancy training strategy.
Okay, thank you.
Yes, sorry, can I also ask a question, even though it seems it already took a lot of time? Sorry for that. So I have two questions. One is very simple, is about modeling actually affine functions. So like, for example, when you do Fourier transformation of a step function or something like that, you may have these problems at the boundaries. Will the same happen here? Yes, right? So maybe my question is, my question is it possible to somehow extend the basis to include affine function as well? But it seems that it's not that trivial.
Great question. So if for affine transformations, then you just need a linear layer. Well, the benefit of Can is coming from the fact that you can use B splines to model nonlinear layers. So I mean, Cans can definitely do that, but it's not. It's like an overkill in some sense, and may also make because it's too expressive. Cans are too expressive. It may make the interpretability, if you care about interpretability, a bit harder than that. But I think you may simply manually build in an extra layer that explicitly learn the linear transformation. Like it can be as easy as a linear layer besides Can.
Okay, thank you. And the second question is essentially about modeling equivariance globally. So the Can, it seems traditionally has an output that is a scalar, so one channel. And if you want to extend it to many channels and for transformations that go symmetrically for those, can we just copy paste it and just like apply in tandem? Or do you think we can go beyond that and also do transformations between positions?
That's a great question, but that's a bit technical. I mean, I'm not I'm not the one that knows a lot about equivariance. I think Hannes must know a lot than myself. But in principle, I think any techniques developed in the equivariant neural network techniques can be transferred to the KART literature. Yes, you can build an equivariant KART, but on a technical level, I'm not sure about how hard that is.
Okay, thank you.